All right, so this is by Abdullah Sharif, and let's just get down to business. We're here to prepare for the end semester exams, AI. All right, it's gonna be a very last minute revision session. Right, I'm just gonna call it last minute revision session. So we're just gonna. The goal of this entire thing is no, I'm not gonna teach you to become a rocket scientist. But then I am gonna let you know what's there in the syllabus and what you need to learn to kind of, score, I would say, more than 80%, right? If you really are unsure about what you're doing. And plus, I'll give you the remaining tips to score that 20% more, right? And where to study and stuff like that. So let's just dive right into it. Cool. So if you think about it, Unit 2 of AI basically deals with search algorithms, right? So why do we even employ search algorithms? Imagine if you had a bot, right? Like Wally, a really cute one, and that's just like traveling from one place to another. And you've given it like this big map, and you've told it like, hey, I need you to go from this place to this place, right? And I need you to find something. So what it essentially is supposed to do is it's supposed to make its way through all these aisles and go and find your wherever you want it to go, or it's supposed to find the shortest path to go to that place. So it could probably go like this, or it could just go like this, right? In a nutshell, you can reduce every problem that you have in navigation, autonomous driving vehicles, to some kind of a search algorithm, right? So diving right into it, you have a few types of search algorithms, and to be very precise, you have 11 extensive types that we're talking about. Cool. So we just start with the most basic type. So I'll give you something that's called a graph, right? So a graph is just a bunch of connected nodes. And if you're like me and you don't know what nodes are just, places on a map, right, that are prominent, and you want to get from one place to another place. Right? So what I'm essentially doing here, I'm calling S the source node and G the goal node, right? So it needs to go from source to goal. Right. So let's first start with our algorithm number one, which is British Museum search. British Museum search. Simple. BMS is very, very simple. Um, you don't know the distances between places. You just know that you can go from S to A and A to B, B to C. So for example, A to E is not connected because there's a mountain in between them, right? A very, very silly example. So starting with BMS, what you would essentially do is you'll say, okay, I'm at S. I can go to A. That's my only option, right? I have no other option. But what if I said, hey, no, you can go to B? Yeah. So now I'd say, okay, fine. Let me erase that. Yeah. So you can go from S to A or B, right? Now from A, yeah, let's look at this particular node. So from this place, you can go to B, you can go to D, or you can go back to S. Now, obviously, if you're searching for something, you wouldn't want to go back to where you were, right? It doesn't make any sense at all. So you're going to look at B or D, right? Let's just write down these two nodes here. So B and D. Great. Now from B, right, you can go to C, A, or S, and we know we don't want to go back to S, so we're going to go either to A or to C. So let's write that down here, A or to C. Okay, and now you might ask me, hey bro, what are you doing here? It seems like you're sorting them alphabetically, right? So rule number one is you write them in lexicographic order, right? What that essentially means is you write them in A, B, C, D in that order. Rule number two that we follow, don't go back where you came from, right? Because that makes no sense. Cool. So now let's look at what else we can do from here. From here, we can say, all right, I have four nodes here that need to be opened, right? So what I'm saying, I have a node, and when I say I'm opening a node, I mean I'm gonna look at the paths that that node leads to, right? So I'm opening S and finding A and B, right? Now I opened A, we opened B. Now let's just go ahead and open all the nodes on this row, right? So we're going to open B to find out that B has C, right? And B can also lead to A as we know it, but then we just came from A, right? So we're not going to go back to A, and pretty sure not going to go back to S. So C, we can go to E, right, down this path. Now, if we were to choose, what else? Yeah, if we were to choose D, from D, we just go to the goal directly. So here, through D, we reach our goal G. There we go. But there's a reason we call this the British Museum search, is that, well, in a British museum there are so many places to visit, right? You have this entire museum with you, and you're looking through, everything. We all know what the British did, guys. Come on, just don't act like you don't. Yeah, so essentially we're going to go ahead and look at all the other possible ways, right? So from A, you can again go to D, and you'll eventually reach G. From C, you could go to E, just like the other one, right? And eventually reach G. Now you might ask me, hey bro, because from B, um, can't we go back to S again? Because we have just, in this line, right? We came this way. We came to B from A. So from A, we went to B. So that just means I shouldn't go back to A, right? I can go to S. Can I? No. So you wouldn't go back to any of the nodes that you've, come from, right? Makes sense. Cool. So see, here from S, you're going to B. Right? This is an entire different path. So in this path, all your nodes are going to be different. In this path, all your nodes are going to be different. Right? But then you're never going to go from B back to S, because that would just be dumb. Cool. So another rule in this is you go through all nodes and do not revisit nodes in a path. It makes sense. Makes sense. Not bad. What if I tell you this is gonna take a lot of time, right? If you have a very big graph, yeah, have fun solving this. So instead, let's look at just another interesting method. So our second algorithm, did I write like a hash for this? Let me have a, there we go, circle to differentiate from the rules that I'm writing. So our second one is your depth first search, and we all know how to do this. So depth first search goes like this. If I have paths to pick, I'll say, okay, I'm gonna start, let's say this is a supermarket, right? And you have these different aisles. I'm gonna start and I'm gonna go all the way in one section of the aisle until I find what I want. If I don't, I'm gonna come back and go to the other section, right? We're not gonna do this fancy thing of going here and then going everywhere. We're just gonna keep going, right, in one direction. If it's not there, we're gonna backtrack, come back, and go in the other path, right? Cool. So the way DFS works for the same graph is we start with source node S. We know that we can expand it to A and B, right? Now we keep going on the left hand side, right? From A, we know that we can go to B and D at the same time. Wait, let me erase that. B and D. And from B, we know that we can go to C. From C, we know that we can go to E. And oops, there's nothing else, nothing more than E. So we backtrack and go back to D, right? Makes sense. Now from D, we reach the goal and we call it a day, just like we would, and stop it here. That's what depth first search does. So depth first search, you trust the path that you're taking, right? The initial path toward the leftmost path in this case. You might be asking, hey bro, what if I choose to order it in reverse lexicographical order? So can I go like Z, X, Y in this way? Wait, you wrote it wrong. Z, Y, X. There we go. And can I choose this path? Absolutely, man. It's just your own way of doing it. But then this is how they do it, right? Depth first search. You just pick a depth and you keep going that way. So in this, you keep going until you reach your goal, right? And you stop at goal. So you keep going down a lane and you stop whenever you see the goal, right? Cool. What's the third one? Right, let's look at the third one, which this was called depth for a reason, right? And this one's going to be called breadth first search. So what BFS was essentially made to do is BFS is going to look at it like this. Is my thing here? No. Is my thing here? No. Is what I'm looking for here? Nah, nah, not here, not here, not here. Then it's gonna go to the second, whatever rack, and it's gonna look at all the second racks of all the, you know, whatever the shelves, and go this way, right? So this is gonna look not depth wise, but breadth wise. It makes sense to an extent. That's fair enough. So in this case, you start with S, right? And you would go to A and B. So let's draw A and B. Now from A, you can go to B and D, and from B you can go to A and C, right? So here I'm just going to draw B and D, and from here A and C. I'm not going to pick one and go all the way down. We're going to pick, go layer by layer. You see what I'm doing here? Yep, layer by layer. Now let's pick B. From B we're going to go to C, all right? From D, oh wow, we reached our goal. Are we gonna stop? Nope. We're gonna keep going until we find all the nodes in that level, right? So we're gonna look at D also after this. Should I do it in dotted lines? Oh, there we go. And from C, I'm gonna go to E, right? Here, the unique rule is stop when goal, but also finish looking at other nodes at same level, right? Cool. That's it. That's your breadth first search. Then you have your hill climbing search, number 4. Hey man, you're using green. Well, I don't care. It doesn't matter. Chill. Right. Hill climbing search. You might be asking, bro, what does this have to do with hill climbing? AI didn't leave even that alone. So the way we do hill climbing, right? Hill climbing is something we call an informed search, right? So think about this. What hill climbing essentially does is it does not look at a very, very stupid simple graph like this. Let me just copy the whole thing. Oh sheesh, that's cut. That's not copy, bro. I know. Relax. So we're gonna go down here. There we go. So instead, we're gonna also add values here. Like why, man? I don't know, dude. You have distances, right? That's what we're gonna add here. So 5, 4, 6, and let me just say that there is no path from here to here, but the distance when you look at it from the top is gonna be this, yeah. So, bro, how do I look at this entire graph? See, it's very simple, right? So imagine you are in Chennai and you're looking at, like, say, I don't know, man, Mumbai, but there's no direct route from Chennai to Mumbai. Yeah, let's just assume that that's how it is. So let's say that you have to go to Kerala, and from Kerala you go to somewhere else, and from there you go to Mumbai, right? Fine. But then you know that from Chennai to Mumbai the distance is 6, but you just don't have a path to go that way. That's this unique value here is called a heuristic, right? This is called a heuristic, and these guys here are just your distance metrics. Cool. Now let's just see how to solve this problem. We're gonna do the exact same thing. Let's start with node S and we'll expand it to A and B. You're gonna ask me, bro, huh, what are you gonna expand now? Now that we know that B is closer to G, because B has 6 over here and A has 7 plus distance. So we're gonna expand B instead of A. We're not gonna blindly follow lexicographical ordering. So we're gonna go with A and C, right? A and C. Now A and C, which one is closer? Both have 7 plus. So which one do we choose? Well, in that case, let's just choose A, because both of these A and C have 7 plus distance to G. Instead, we're going to pick the lexicographical one as a tiebreaker and expand A to D and D to G, because that's the only way we can go. So here what we do, we choose and expand shortest path, right? And wait, did I mention that we backtrack here? Yeah, we backtrack when needed. This is backtrack, right? Cool. There we go. So you choose and expand the shortest path here, right? So this does not guarantee the optimal path. It just guarantees that you're not gonna blindly go and lexicographically choose cities, right? Because that's just dumb. When you have data, you use that data, right? Bro, what is the data here? These values. Cool. Now, why do we go with this algorithm? Number one, I don't know, man. It's just faster. I'll tell you why this algorithm sucks in a few ways, right? I'll tell you the disadvantages or the problems. So number one is local minima. Local minima is when, let's say, you come to A, you know from A to G is the shortest path, but it forces you saying like, no, pick B because B is closer to G, right? But then this is just a dead end. You're not going to go anywhere from there. So you might get stuck in a local minima, right? And you might have to look at all of the paths. So let's say if you had more nodes this way, right, and they were actually not leading to the answer, you would have to go, and come back. So let me draw that in red, and come back and go here and come back and go here and come back and go here and come back, and at the end you'd reach your goal, right? So what people in the computer science domain, like as if it was not hard enough, they like to call it the telephone pole problem, right? But the advantages of this is that we're not searching exhaustively, right? We're searching with information, right? And that's just helpful. Cool. Now let's look at our fifth algorithm on the lineup, and that is beam search. I want you to look at hill climbing search and just look at it as a daddy of depth first search, right? Because this just uses heuristics, and this is dumb, right? It does not look at any heuristic value. Right, now for beam search, let's start with S. You know that we can go to A and B, right? Now from A, you can possibly go to B and D. Also, at A, you know that the value is 7 here, and at B, you know the value is 6. Let's also write that down, right? Because why not? So 7 plus and 6. Right, so from A, we're going to choose B first. Let's just not choose A. Where is it? B. Because it's 6, right? We don't want to choose the higher one. From B, you can go to A and C. Bro, you should have memorized all of this by now. Oh, come on, man. Yeah, A and C. And from here also it's 7 plus, 7 plus. Now, before going into this depth, right, I'm going to first finish exploring all the nodes on the previous depth. And let's go ahead and expand this. We're going to get B and D respectively. Here, D has a distance of 5 and B has a distance of 6, right? Now, we're going to choose D and we found G, our goal. Right? And we're going to also proceed to all the other nodes in the same depth, and we're also going to look at B, and we get C, which is not the goal, therefore terminate. Right? Cool. So you might be asking, bro, just why are we even doing this, man? I'll tell you what. So the uniqueness of beam search is that you have a value called beam width, width, right? And you can choose its value. So a beam width is essentially like this. It's like saying when I have a graph of so many nodes, right? What we are essentially doing here is saying, hey, I don't want to look at all the nodes. Just show me the nodes closest to my goal, and let's say my goal is somewhere over here. So we're telling it if the distance from here is 1, 2, 3, 4, 3. If our width is 2, we'll pick the two closest paths, this one and this one, right? And we are only going to explore those paths. Just like a beam on a flashlight, right? If this was a flashlight, then we would only look at this zone of on our graph. And that's why it's called beam search in the first place. Yeah, just in case you were wondering. But here, the width of our, when we expand the nodes, it's just the same as width is equal to 2. So it doesn't make sense on this graph, but it'll make sense on other graphs that you're going to work on. So relax. Right. Now let's go on to our sixth one, which is our oracle. Okay. Our oracle is essentially this BMS, dude, but with info. Right. So what does that mean? You start with S, you go with A and B. I memorized it now. From A you can go to B and D, and from B you can go to A and C, right? But then bro, you said you were going to use info, right? Why are you going to use info? So let's look at the distance traveled. So from S to A we're traveling a distance of 3, S to B we're traveling a distance of 5. Let's write that down. There we go. Distance of 3, distance of 5. From A to B, A to B, get it? So from A to B we're traveling 3 plus 4, which is 7. And from A to D we're traveling 3 plus 3, which is 6. Let me also write that down. So this is going to be 7 and this is going to be 6. And this should be 9. This should be 9 also. And if you keep expanding, you're going to get B, C, E with a cost of 11 and 17. You're going to get the goal here with a cost of 11. Talk about memorization. And you're also going to get the goal here with 17. Yeah, I'm totally looking off my phone screen, so relax. Now from C to E, 15, right? So just look at what's happening, right? We're going to take the entire graph, find all the possible ways that we can go here. What's the use? We have info this time. It's just BMS, but you have info. So now you know my goal can be attained at 11 is equal to cost, right? So you know that you can get your goal at 11. It's almost like bargaining. So I'll tell you where we use this algorithm, right? Let's go on with algorithm number 7, which is branch and bound, B and B. So what branch and bound essentially does? Well, one way to find out. Let's just steal the graph from here because I'm just sick of navigating through pages. There we go. Yeah, save some time. Beautiful. Now we're going to start with S like the usual, right? We'll go with A and B. And we know that to go to A takes cost 3, to go to B takes cost 5. And obviously we're going to go to here, B, right? And D, because A is like the shorter path. And B takes 7, D takes 6. And again from this B we're going to take A and C, and it's going to be 9, and it's also going to be 9. Now from B, right, we're going to go to C because, oh wait, sorry, we're going to pick D because D has the, so the thing about branch and bound is you first branch, right? You first take all your branches, then you go into a branch with the lower cost and you open up the nodes there, right? So you open it up in the order of cost. So I'm going to open this. I'm going to find G. Now my G, I'm going to get G at cost 11. So that means essentially I know my oracle equals 11. What does this mean? It means I can find my goal with a cost of 11. Then why go further, right? So what I'm going to do here is let's expand the other nodes, right? So B to C, but the cost of C is 11. So terminate. And we still didn't get our goal. A to D, cost is 12. Terminate, because we still didn't reach our goal. And same with E, it's 15. Heck, we're not going to go there at all. Right? Terminate and terminate. And why do we terminate? Because the cost is greater than the oracle. Greater than or equal to the oracle. And you still haven't found the goal, right? So makes a lot of sense. Now let's move on to our eighth one, which is branch and bound plus extension list. Okay, hey man, you should have told all the algorithms that are there in the first place instead of going, endlessly. I mean, chill. I said that there are 11. We're going to look at all those 11. Yeah. So look at branch and bound, right? And you might tell me, hey, bro, look, it's just dumb. From S, you went to A to D to G. Do you not realize that you're doing the same thing by going from A to D and you're going to find G here? So you're just going through the same path just via another route, right? And that makes zero sense. So, well, I'm going to ask you, what are you going to do about it? So you're telling me that you're going to have an extension list, right? Something called an extension list. And you're going to fill it up as you go. And you're never going to come back to those nodes again. So I say, whoa, damn, okay. So you start with S. You go to A and B. You can go to A and B with a cost of 3 and 5 respectively. I'm going to expand A to say that there is B and D, right? And from B, I'm going to say that there is A and C. We still didn't find our goal, but we're going to keep going, right? Now, once you open S, you're going to write S here. Once you open A, you're going to write A here. We open B, we're going to write B here. Then we open D and C in that order. We're going to write those also here. Now, when you look at the next node that we're supposed to open, we're not even going to consider B. Not even going to consider it. Stop it. Because you've already extended B here, right? We're not even going to go through B at all. So now, D takes 6, A takes 9. We're not going to go through A because we already have A open right here, right? What else? C takes 9. We just open C. So yeah. Then from here, we're going to go to G and find the goal. And we know that this is our oracle at 11. And here from C to E, we're going to stop because the cost is 15. And this is our list, right? So we're going to add G and E there on that list eventually. So we will never come back to these nodes. You just see how many nodes we saved. Bro, I really can't see how many nodes we saved. Well, I'll show you how to look at that at the end, right? We just go ahead, stomp through this. So algorithm number 9 happens to be branch and bound plus estimate heuristics. All right. So let me get one thing clear. Bro, you've been saying this is called a heuristic and this is called a cost, right? But what does that actually mean? So by that I mean, to go from node B to node G, you need not have a path, but you know that your estimated heuristic is 7. Right? You would go, 6. So you would go from B to G if you had a path in 6 cost, but you don't have a path. So this distance between A and D where you have a path, this is called a cost, right? Remember that. Cost versus heuristic, right? Are they going to ask you this question? No, but it's just better to know it. So yes, let's say branch and bound plus estimate heuristics. So estimate heuristics just means cost plus heuristics. Bros, how do we do it? Right, let's first order of business, copy this beautiful graph here. There we go. Alright, so the way we're going to do it, we're going to start with S. Hey, there we go. And it's going to open A and B. And since we're considering both cost and heuristics, from S to A, the cost is going to be 3 and the heuristics is going to be 7 plus, which will lead you to an answer of 10 plus. And for B, it is 5 and the distance from your goal is 6. So do you see how this works? Every node you jump to, you're looking at, hey, I've traveled this much, but I am so close to my goal, man. I swear this is very close to my goal. So you go down a longer path, but then this is closer to your goal. You go down a shorter path, this happens to be a little longer to your goal, right? But at the end of the day, with the trade-offs and all of that, it's going to be 5 plus 6. Hey man, right, yeah. Which is equal to 11. And 11 is greater than 10. So damn it. Bad juju there. There we go. 10, 5 plus 6, 11. Beautiful, yeah. Now we'll expand A. We're going to get B, right? We'll expand this to D. And D is going to be 6 plus 5. Bro, how did you get this? Listen, look. From S to A is 3. From A to D is 3. So 3 plus 3 is 6. And the remaining distance to go to G is 5, right? So if you don't have a... 1 minute. So let's write this here. If you don't have heuristics, use shortest path to goal as heuristics. So what that essentially means is if I did not have these heuristic values here, right, I would just calculate my distance from C to G as the shortest path from C to G, which is going to be 4 plus 4, 8, 8 plus 3, 3 plus 5, right, which is 24, right? How do I get this erased? There we go. Cool. So if you look at a graph and there's literally nothing, then this is what you do. Great. Now from B, you can go to A and C, right? All right. Now to go to, let's say, so this is going to be 6 plus 5 equals 11. And this is going to be 16 plus. This is going to be 16 plus. This is going to be 13. Let's expand D because D is the shortest. And you're going to get G, where G is your oracle. And you know that you've taken 11 paths to come here and you are at your goal. So the heuristics is 0 because you are at your goal. You don't want to expand this, this, and this because they are longer than your oracle, right? Makes sense. Cool. Now you might say, hey man, we just learned about this extended list thingy and why aren't we using it here? Well, you could. So that is what we call A star, and that is our 10th algorithm, right? A star is nothing but branch and bound plus estimate heuristics plus extension list. All right. So what this essentially means is you see here how you've calculated this 16 plus value. Instead of calculating it, if you know that A is in your extension list, you're gonna stop. You're not even gonna calculate that value because calculating it has some computational cost, right? There should be some reason why A star is better than A, right? Better than the other algorithm, and that's why it's better. So the way you would do this is same thing. You'd start with S, go to A, go to B. I'm just gonna speed run through this because it really doesn't matter. Do it yourself. This is going to take 10 and 11. It's going to be 3 plus 7 plus, which is equal to 10. This is going to be 5 plus 6, which is going to be 11. And this will take you to B and D. And wait, that's a D. This will take you to A and C. And C is 16 plus. B is 13. And D is 11. Wait, you don't need to calculate B, right? You're just going to terminate it here. You're going to terminate it here. Just like that. Don't even calculate. And you're going to get the oracle here. Right, so you stop C. You get what I'm trying to say. Here you terminate it, right? Terminate it since greater than or equal to oracle, and you terminate this since it is in extension list. Great. Now you might ask, hey bro, like that's all right. I mean 10 algorithms. Nah man, this is just the last one, the 11th algorithm, and it's just called best first search. Essentially what this is, it is like it is DFS plus estimate heuristics plus extended list, which the probability of it being asked close to 0, bruv. So just relax, I'm not gonna ask, right? So these being the 11 algorithms, if you want to know more about it, just go to geeksforgeeks.com or just type this in Google and look at images. You'll get a pretty fair idea of what's happening around, right? Cool. That's that. And You want to look at a question, huh? All right, why not? Right, so they told us to solve this with branch and bound. So what we're gonna do, so let's go from initial state A. It's going to be fairly simple. So you start with A. From A, you know that you're supposed to use branch and bound algorithm here. So from A, you can go to B and you can go to F. And in branch and bound, like so, you use your cost, right? So we're going to use our cost of 6 and 3. And obviously, we're going to expand F here, which is going to go to G, which is going to take a cost of 4. We're adding up costs here, right? Just remember that. And this is going to go to, hey, I might need to downsize this, don't mind me. Right, from F you can go to H2. H is going to take 10, right? Now from all of this, man, yes, we're going to keep going. All right, so the lowest cost is G. From G we're going to pick I. That's the only way we can go. And there's 3, so 7. Now the lowest path here is 6. So from B we can go to C or D. From C, so this is 9, and to D it's 6 plus 2, which is 8, right? Now the lowest cost here is 7, which is I. From I you can either go to J or you can go to E, and J is going to take you 7 plus 3, which is 10. There we go, fairly simple. And at 10 you get this guy, right? Now as we do in branch and bound, we know that 10 is our oracle. So what is the cost to E now? From 7 plus 5, which is 12. Therefore, terminate. More than 10, terminate. Let's look at D. From D to E, it takes 8. So 8 8s are 16. Terminate. From C to, you can either go to E or D. If you go to E, it's going to take 14. If you go to D, it's going to take 10. Terminate and terminate. Right? Beautiful. Now at the end, I want you to write down a table, right? A table which says number of nodes expanded, right? Number of terminations. So the number of nodes here are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there are 13 nodes on our graph right now. Number of nodes expanded 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6, 7. We expanded only 7 of those. And number of terminations 1, 2, 3, 4, 5, which is the remainder 5. Right? So if you were to use different algorithms, right, you would essentially try to compare them by drawing this table, right? And you would compare branch and bound, then you would compare branch and bound with extended, whatever that is, right? There we go. That's it. That is entire graph algorithms for you. You're welcome.